begin. So homework questions. A few things have come up in terms of troubleshooting, and I don't think I made this point as explicitly as I wanted to. So I wanted to pull up an M+ file and alert you to a couple of idiosyncrasies with this program. So M+ has a rule that it will stop reading your line of text after 90 characters. It will give you an error message that says, it's over 90 characters, I don't know what to do. There is a tiny little number in the right corner that tells you where you are. So if you're not sure if your lines are too long or not, for instance, I'll go out here. Where my cursor is column 88. If your comments go past 90, that's okay because it's not reading them anyway, but the main text has to stay within 90. Now where this starts to be a problem is when you have a situation like this here. So this is a situation single factor model like we had in our example, where you want to start putting in constraints, right? So let's purposefully make these long so we can see what happens. So I helped a few people who had code that looked something like this. Technically nothing wrong with this, except that by the time you get to this point, you're in column 92. So it's not going to understand your sentence. The easy thing to do would be to do this, right? No, that won't work. The constraints only apply to parameters that are mentioned on the same physical line of code. So if you have a list of model parameters that wraps around like this, and you have your constraints after it, it doesn't know what to do. So if you're in the situation where whatever you want to do is past one line, here are two options. One is to split it up so that each set of constraints is on one line. So you would do something like this. There. So each line is its own command. Each line ends in a semicolon, and the three constraints, or the three labels, apply to the three parameters there. So that's cool. If that seems like too much work, and I'm right there with you, let me introduce you to something called find and replace. Control H. So you can shorten the names of your variables and the names of your constraints. M+ doesn't know what your variables used to be called. So I saw several of you who were typing out GPS and GPSR. You don't have to do that. So if you do find and replace, for instance, I have this sit as the prefix for all of my items. I can just replace with an S, for instance. Now there's a match case button here, by which it won't replace all instances of sit, just the ones that match the case, and you can have it do just in the selection. So that cuts that down. And I could do the same thing. So if you don't want to type very much, you don't have to use longer labels. You also don't have to use labels that have these R's at the end because it breaks up your ability to refer to these things parsimoniously. So there's nothing wrong with doing this, S1 to S6, and then referring to that. Another thing that I've been noticing is that some of you are faithfully recreating my example, which is great, except that that means you're typing more than you have to in certain spots. So all you really need to type is this much. And actually, these stars are unnecessary. I have them there for completeness. What you have to type is define which items go with which factor. The first factor loading is fixed to 1 by default. The star overrides that default to estimate it. Factor variances are estimated by default. The @1 overrides that default to fix it to 1. And actually, the last part is unnecessary too, because factor means are 0 by default. So that's really all you have to type until you get to the point where you're computing omega, in which case you have to label the loadings and label the error variances and any error covariances. The reason that I type everything out is for completeness. That way I know what all I've asked for. I don't have to memorize what the defaults are. And pedagogically, it helps for us to go over what are all the model parameters. They all have ways of being referenced. So, questions on that? Anything else in homework 2 that's come up that I can help you with? No? So, Jihong, you were helping someone figure this out in Levon.
Yeah.
Did you figure out what the difference was between M+ and Levon?
Actually, I didn't know the real reason for that, but when I use the formula to calculate the zero parameter model skill correction factor, I can use that formula to recalculate that.
So the nested model comparison is not, the number's off.
Yeah. Every other estimates are correct.
Okay.
Match M+, but only that scaling correction factor is not.
It's a different number?
Different.
Okay. So for those of you who've learned R or want to learn R, so far we've found that you can do all of homework 2 in Levon, the structural equation modeling package in R, with the exception of their scale factors are not exactly the same as M+'s, and therefore your -2 log likelihood differences to compare nested models don't work out to be exactly right. But they're close, right? It's just a question of precision. They're not close. Okay, never mind. So then you have to decide if you believe Levon or you believe M+, right? I don't know, but for sake of consensus, we're doing M+. So, question? You have lots of homework. Okay. Okay. Let me pull up homework. Yes. That's one of my favorite questions. Maybe not yours, but it is mine. Okay, number 23 is the question here. Nope, 25? 25. Is that it? Section 325. So what is the sign difference between the model CFI and a perfect CFI? What I'm trying to emphasize here is the value that you found lower than it should be or higher than it should be? That's what I want to know. So when I say signed, keep in mind, should the CFI be big or should it be little? So answer my question, folks. Should CFI be big or little? Should be 1. Should be big. 1 is perfect. In contrast, things like RMSCA, SRMR, those should be little, and 0 is perfect. So I want you to look at the number that you have and tell me, is it too small or too big? If it's too small, then it should be a negative difference. If it's too big, then it should be positive. Okay, next question. Okay, you write that down, and I'll answer Betsy's question.
Yeah, I'm not sure if this is more appropriate to ask you here, or if it's better for me factoring office hours, but with also in part 3 of the homework, I was having a really hard time finding the normalized residual for the variance of an item. I don't know if it's something I have to compute, or if I just can't read my output correctly.
Or you haven't scrolled far enough.
Yeah, I don't know, because I'm able to find normalized, residual covariance, but I can't find it just looking at it itself.
Okay, let me get, I think this is the model. Actually, no, this is your, not your homework, this is the example we did in class. So this is a one-factor model. So in the M+ output, you'll see why I build handouts rather than printing out these 97 pages. I know of no way to shut off the extra output, by the way, otherwise I'd show you. So after all of this initial stuff, it tells you how much missing data you have, it gives you descriptive statistics, then comes model fit, then comes unstandardized results. Note that it's just called model results. It's up to you to know that it's unstandardized. Then standardized. Then we get to residuals, where you get lots and lots of tables that look the same, except for you have to figure out within each section what it is. So the first section here are model estimated means and residuals for the means, standardized residuals for those means, and normalized residuals for those means. We then get into the same thing with the covariance matrix, model estimated covariances. That name is insufficient because what is in here is not just covariances but also variances. So this would be known more completely as a variance covariance matrix because the variances are on the diagonal. The covariances are on the off diagonal. So this is what the model says they should be. This is the correlation version of that matrix where the variances have been replaced with ones on the diagonal. Then we get to residuals for covariances, which is not residual in the sense of not the factor, it's residual in the sense of discrepancy. It's mismatch between model and data. So this residual for covariances is how far off each covariance is in a covariance metric. The text wraps around, so here's the last column and row of what should be a 6 by 6 matrix. Here is how far off each of the correlations is, which actually is a new piece of output I don't remember seeing before. Here's the standardized version, and then finally we get to the normalized version, which is the thing you've been looking for. And I think this is on about page 26 of the output by now. So normalized residuals for variances and covariances, where the same thing would apply. So these are discrepancies between model and data put into a z-score-like metric, where anything above 2 or 3 in absolute value would be indicative of a problem.
Doesn't it say it's 0?
Yes, it does. And is that why you were confused?
Well, that's right.
Uh-huh. So why is it right is the question. That's why I'm asking you to find that, to remember this. So we're looking at data model discrepancy, right? So the variances are perfectly reproduced. They have no discrepancy, so long as what is true.
Oh, they're the, like, they're their own mean, or like there's a baseline?
Right idea, wrong word. They get their own other one.
Oh, other one. I don't know what it's called.
Someone help her.
Residual variance?
Yeah, residual variance, yes.
Okay.
Yes. So these variances are going to be perfectly reproduced because each item gets its own residual variance to plug the hole to get back to total, where if it's factor, residual, and then total. So that, in asking you for that number, that's the point I'm trying to get you to remember. Variances are perfect. Likewise, means are perfect so long as each item gets their own, say the word again. The one you said wrong is right for this answer. There you go, yeah. The item means are going to be perfect so long as each item gets their own intercept. So yes, I'm trying to drill in that as a point. And I think Adrian had asked a question a few weeks back, when wouldn't you do that? Very few cases. We looked at one last time, tests of tau equivalent items or parallel items. Parallel means that you constrain all the residual variances to be the same. The only time the intercepts would be the same would be in terms of like a growth model where you're trying to test whether things change over time. Those are the only ones I can think of off the top of my head. Okay, does that help? Okay, now Heather, you had another question? Yes. That is, what question is that? 27. Oh, yes. So I'm trying to get you to remember the definition of absolute fit for RMSEA versus close fit. So what is the best possible RMSEA that one can have? 0. What is close enough? It's fine. That's close fit. What is it? 0.05. So how far off you are will be different for each of those standards. Okay, other questions? Yes?
Because it's fine if, like,
So Google University led you astray? What did the internet say close fit is?
I think we find the other thing like they feel like guarantee is absolute.
It's absolute in the sense that it's relative to an answer key covariance matrix, whereas relative fit would mean just one model is better than the other, but we don't know in absolute sense how good they are. The term close fit is, it goes into this RMSEA confidence interval, and so it has a specific definition by the people who invented it. And this is what this confidence interval and this probability that RMSEA is less than or equal to 0.05, that is known as the test of close fit in this specific context. I don't know of any other fit statistic other than chi-square that has some kind of distribution with it by which you can compute a confidence interval. So if you want to send me whatever you found, I can try to take a look at it and see if it's different context or if it's just a different way of explaining it. What else? Yes? Which question are you looking at? Yes. It is the chi-square value that comes from the rescaled log likelihood difference. So it's in the spreadsheet. Let me pull that up here just a second. It's thinking about it.
So do we have to compare this value based on saturating model or the only?
Well, it depends on the question. So for instance, the definition of absolute fit, how your model fits relative to the saturated perfect H1 model, I computed for you as an example. So this column, the scale difference in chi-square, that's the test statistic. And by the way, it's these numbers right here that differ between Latent and M+, and that's why this result differs. So then when you compare subsequent models, such as a 1-factor versus a 2-factor I had done in this example, this is the test statistic for whether the 2-factor model fits better than 1 or whether 1-factor fits worse than 2. So it depends on how the question is phrased, which way you're talking about it. In the context of your homework, I asked you to add a model parameter. So whenever you add something, the model has to get better or not better. If you take model parameters away, such as when you test for tau equivalence, then it's worse or not worse. So it just depends on what is the reference model, and you're adding to make it better or taking away to make it not worse, hopefully. Does that help? Okay. Who else? Betsy again.
Okay, yeah, sorry, another question.
It's okay, they pay me.
Okay. With EPSY quick 3 again, looking at test statistics for unstandardized loading, I thought I knew what a test statistic was, and now I'm thinking I don't.
Okay.
My answer is not right. But how a test statistic, that's the p-value.
Nope.
No. Okay, then yeah, I don't know what it is.
Test statistic is a T, a Z, if you're testing. It's either a T or a Z if you're testing one thing, or it is a Z or an F if you're testing more than one thing. The difference is whether or not you use denominator degrees of freedom. M+ does not, and so everything is either a Z or a chi-square. So for a single parameter, An example of a test statistic would be, like if I look at this output right here, the estimate divided by the standard error is this third column right here that is unhelpfully labeled estimate over standard error. What that actually is treated as a z-value, and that is a test statistic. Given that z-value, this is the p-value that is associated with it. Does that help?
I feel kind of like someone, you know that like Chinese box where you just like learn all these symbols and what they mean, and then you don't understand what they're doing?
No, but I'm picturing like Orphan Annie decoder ring or something along those lines.
Like I don't know. It's like a bigger question.
Yeah, you're feeling like this is unfamiliar, and you're feeling bad that it feels unfamiliar. Is that?
I'm just feeling like I don't know. It just is like, who decided that was what we should be doing? Now, it's like, why is it called a test statistic in this scenario but not other ones? And then the cynical part of me is like, I really want to learn this because I just want to like hire a statistician.
Oh my goodness. So let me address each point of those.
I'm dropping out of grad school.
No. So who decided this and who said we should do it this way? You should talk to Tyler because he's Captain Bays right now, and he would say, I agree, this is ridiculous. Right? Something like that? Something like that. So yes, this is a frequentist version of estimation in which you have these t-values and you're talking about the limits and infinity and if this study were replicated 8,000 times and these sorts of things. So that's more of a theoretical argument that I'm sticking with frequentist because that's what everyone I've taught has been exposed to. At some point in your career, it would benefit you to learn the same things and how estimation interfaces with that in terms of using something like Bayes instead of just straight up ML. I don't want to learn this. It's hard. You're not wrong. This is why they pay me, and this is why you're here. If this was something where you could pick up a book and be in 10 minutes be like, yep, got it, we wouldn't need these classes. And that's not a knock on you. I had to struggle way hard. You guys already know way more than I did at your point, and it makes me very happy to say that. But my guess is that you, like a lot of other people in this room and that I've taught, are used to things coming easily. You were always good at school, right? That's why you kept going in part, is because you're good at it, you like it. You know, it's fun to do things you're good at, and this is a struggle. It really is, though. It's not just you. I think you're one of the few people who's been vocal enough to share. But who else feels like it's a struggle? But I'm putting myself in this list, by the way, because at this point in my career, I still can't just look at something at 10 minutes and go, no. I get manuscripts to review. I'm the associate editor for a quantitative journal, and I am always given things that I can't understand. And now what I get to do in that situation is say, you know what, it's the author's job to write it in a way that it's easier for me to understand it. Because if the editor thought that I had enough expertise to judge this article, and I don't know what the hell you're talking about, then it's on you, not me. So there's a sense in which it's great that you're willing to say this, because it is on me. And I'm going to try my best to use different words or different examples until things start to feel a little more familiar. Now, the very last thing that you said, hopefully tongue-in-cheek, is that you're just going to pay someone to do this for you. So, unlike many other fields, there is no statistics certificate. There is no program of quality assurance that you can say this person is, you know, FAA accredited, or this person is. What do teachers go through, right? Certifications. Accountants are certified. Garbage men are probably certified. But statisticians, you can just stick a sign on your door and say, I know what I'm talking about. And because you don't know the difference, you have to trust. And that is a very dangerous situation to be in. Now, it's perfectly fine if you know that you're not going to be the one who wants to keep up with the latest developments in quantitative psychology or quantitative methods, because that's not your primary focus. but at least having been through this experience, you can maybe follow the description of the statistician and read what they're doing and know enough to ask the good questions, even if that's not going to be what you do the rest of your life. But I will tell you that knowing these things will make you more competitive for any job that you are looking for in the future. Even if you hate it, it is a valuable skill. And for no other reason than that, I would say, please don't quit. That's my impassioned plea to all of you. So I'll get off my soapbox, but I have so many former students who were like social psychologists or business people or people who just, they had to take methods as part of their curriculum, but they ended up getting jobs crunching numbers, and they're better paid than I am. Like that's, because that skill is so important. Data science is how it's being rebranded in today's market. It's one of the fastest moving careers that you can sign up for. No, seriously, data science. There are certificates and degrees called that now. But statistics is a big part of that. So anyway, yes, it's hard. So is anything at first.
I have a related question. Since, like,
now I'm getting all sweaty.
Wait a minute.
Getting worked up.
Like, what is a test statistic? Sometimes I do feel like, okay, I understand these more complicated things, and then I'm like, but what's a standard error? Like, sometimes that's hard to hold on to. Like, you get wrapped up in the more complicated stuff, and then sometimes you're like, wait a minute, but what's
standard error is, so you know the taller? There's a likelihood mountain that goes with each of these parameters. Standard error quantifies how steep the mountain is, inversely. So it is a byproduct of the estimation process. It reflects the second derivative with respect to the function. But loosely speaking, here, I'm going to get out paint again. I can't go to the board because the 6 random people from around the world who watch this will be really disappointed in me. Okay, so if I gave you a distribution that looks like this, you would feel a lot more comfortable saying, yep, that one is the tallest, than something that looks like this. Right? That's a little lumpy. Let me try that again. Yep, tallest is right there. Standard error is the inverse of the steepness of this, basically, where a really high standard error would be associated with the plot on the right, a really small one would show up on the left. Beyond that, Craig Ender's chapters that I put on the reading list, chapters 3, 4, and 5, I have found to be the clearest description of likelihood and derivatives, especially what robust maximum likelihood does in terms of where that scale correction comes from. I would recommend rereading that as many times as it takes for it to make sense. Again, it's not something you're like, 10 minutes, I'm good. At least that wasn't my experience. So, all right. What else can I help you with? Heather. No, you have to comment it out. That's how you keep multiple models in the same file, and then you have to rename the output file if you want to save it. Otherwise, it gets overwritten every single time. Ostensibly, they introduced a way to block comment, like in SAS, how you can put one at the end and one at the beginning. I've never gotten it to work. So put an exclamation point at the beginning of each line, and that keeps a record of everything, but only runs the thing that's active. Okay. What else? All right, are we ready for something new then? Something that I hate to say is even harder a little bit, but it's fun though. I have pictures and stuff. IRT is fun. This is lecture 5. Let me, I'm going to actually change videos here and pick up with a new one since it's a different topic. Come on, you can stop. No. All right. So a little backstory behind this lecture, and we'll start off with a little review, but then get into IRT. So I had the opportunity when I was a graduate student in psychology at KU in the early 2000s to take IRT from Susan Embritson, who is like the doctor genius of the field. Like she's one of like the really big names. And I was so worried about looking stupid in front of her that I went through the entire semester not knowing what the hell a logit was. She talked about logit about every 30 seconds, and so it's linear in the logit, and the logit is good, and I don't know what the fuck a logit is. And so that's the start of this lecture, is making sure you guys know what a logit is, because if that's not clear, the rest of this is going to make no sense. And so that was an example of something that I worked really hard at. I read that book so many times over and over again. I tried to run these models in my dissertation, realized that I knew nothing when I actually tried to do it, and I still know nothing, but I keep trying to do more. So this is something that I actively work hard at as well. So don't be afraid to look stupid. Because you're not stupid, you're only uneducated if this is your first exposure. So where have we been so far? Big picture. Classical test theory, what I refer to as the add shit up model. The idea is that we take our items, we create either a sum or a mean of them, and that summary statistic, that sum or that mean, is supposed to be our best guess as to someone's trait. In so doing, we assume unidimensionality. In trying to characterize the reliability of that estimate, we also then assume either tau equivalence or parallel items, no error correlations, and all that other stuff. In addition to those assumptions not being testable within this framework per se, the problem is that the items are inherently tied to their sums. So in order to be able to compare someone's test score across multiple samples or across time, you have to give the exact same items. And not all items are going to be as useful for certain types of samples. And so what you can do, practically speaking, is greatly limited by the fact that you're dependent on the sum being a representation of the trait. So what do you do to make your test, your score more reliable? Get more items. What kind of items? Just more. More is better, right? More makes alpha grow. And then we talked about CFA. CFA changes the ballgame into an item level model. Now we have a separate trait that is not just the sum of the items. Each item is characterized by three things: intercept, loading for how related it is to the trait, and error variance for how much of its total variance is due to not the factor as opposed to the factor. Each person is characterized by a single latent trait estimate in this model, or multiple latent trait estimates when we have multidimensional models, that then, in theory, cause them to answer the questions the way that they did. So by breaking this tie between the items and the persons, I can have comparable trait scores, these Fs, even if not everybody gets the same items. That means you can have missing data. That means that you can deliberately give different versions of a test to make sure that your test is as meaningful for certain types of people. We still assume this idea of local independence, meaning that the trait is the only reason that these responses were related to each other, unless you extend the model to have error covariances, which are then part of the model. They are unexplained multidimensionality. There's some other reason why the items are related in that case. And if you want to make your test better, you don't just need more items, you need more better items, because items differ in their loadings. Not all items are created equal. So if an item is better, it's better for everyone, because the slope is linear. The expected change in the item response as a function of a 1-unit change in the factor keeps going all the way across the factor. So items with stronger slopes are better, the end. That is not going to be true anymore. Because items with stronger slopes are better, the end, that translates into an assumption of constant reliability across the trait. So I showed you how to compute omega, right? You get one number that's supposed to summarize the entire trait's reliability. That's not going to be true anymore either. So those are some big conceptual differences between where we're headed and where we've been, this idea that you can have an item be better for everyone. So if you have had some coursework on generalized models, this will sound very familiar. If you haven't, this will all sound brand new, and that was the situation I was in when I took this course. So we talked about the analogy of regression. So confirmatory factor analysis is to regression. Confirmatory factor analysis is like X is latent. and in regression, X is observed and it's sitting in your data set. In the same way, the models we're heading, which fall under two names, item response theory or item factor analysis, is the analogous to other kinds of regression for not normal responses, such as logistic, probit, or multinomial. So if you've had me before, I've spent like 2 weeks on this, which is completely inadequate. How many of you have had coursework in this box right here, logistic, probit, multinomial? 1, 2. Do you feel like you're good at logits, Lucas? Or you've just seen them before?
I feel like I'm getting a motor out there.
Yeah, it's not very intuitive, right? And this has been the modal student in all of my classes has never had coursework in this. And it is impossible to understand IRT if you don't understand logistic regression. So we're starting there. Oh, deal? So, stepping away from the world of measurement, just getting back to this idea of what the hell a logit is. The world of generalized models. So terminology, general means your residuals are supposed to be normal. Generalized means there's some kind of not normal, some other kind of known distribution. So we're talking about regression models for not normal outcomes for a few minutes, just to get this idea so that we can then talk about how these same concepts apply in the context of latent variable measurement. So there's 3 things that characterize these models. One is that we're assuming that our outcome follows some kind of not normal distribution. And there are lots and lots of options for what not normal is. Bernoulli is what it's called if you have something like a binary outcome. If you have something like a count outcome, it would be called Poisson, for instance. If you have a number correct, binomial would fit that bill. So there's lots of different choices besides not normal. The second piece here is what's known as a link function. It means a transformation. The trick is that we're not transforming our data. We're transforming the outcome that the model predicts. And link functions are things like logits and probits and tobits, and that's all the other its I can think of. Log, complementary log, all of those things are called links. And then finally we get to the part that you know already, the linear predictor. That's what's on the X side. So how you put in predictors, they can have fixed and or random effects to then predict some kind of outcome. So the third part here is not new. We're going to end up at the end of this with something like an intercept and a slope, just like we had at CFA. It's the other parts that make this different. Okay, with me so far? All right, so here's an example. What if I hadn't had coursework on generalized models and I tried to predict a binary outcome using just a regular old regression? Let's start there. So terminology. And this is something that took me a very long time to get right, and I'm not sure that it is right, but it's closer than it was even a couple of years ago. If we have people who only have 0 or 1 as a possible outcome, what the model is trying to predict as the expected mean, the expected value, is actually the probability of one or the other. I think of it as easier to do one, so let's say that. So the conditional mean or the expected mean is the probability of people that we have a 1. That's the thing we're trying to predict. So that's why I have P of y equals 1 there, probability. Then after that is my regular old linear model, what's known as the linear predictor, and my residual sitting at the end, which is how far off my model prediction is from the original outcome. So in this situation, we would know what to do with these betas. Beta 0 would be the expected probability of a 1 when these predictors are 0. The betas would give us a 1-unit change in the probability of a 1 for a 1-unit change in the predictor, and E would be the difference between the observed binary value and the predicted probability. So it looks like this. So there's 3 reasons this model is broken. Number 1 is that it's a linear model. So if I plotted a linear effect of X on a binary outcome, so the y-axis is actually probability of a 1 here, the linear model keeps going. So even though it makes no sense at some point at high levels of x, the probability of a 1 that the model predicts goes above 1. And at some point on low values of x, the probability of a 0 goes below 0. That can't be right. What we need is to understand, to make the model understand, rather, that the slope has to kind of shut off. It has to asymptote at both ends so that it knows that it can't predict anything above a 1 and it can't predict anything above a 0, below a 0. A link function is how this squishiness happens. So here's how we fix it. Rather than predicting the probability of a 1 for a binary outcome directly, we transform what it is we're predicting. And when I say we, I mean the software does it. You are not transforming your data. You still just got zeros and ones as your outcome. Software does it through your instructions. So first, conceptually, the inside of what this thing is going to become is what's known as an odds ratio. The probability that y is 1 over the probability that's 0. But odds ratios are skewed. They're bounded by 0, so we can't predict odds either because odds can't go past 0. Odds, I don't understand. I'll just tell you that. I've never understood them, and I never will. I've just given up on odds. But in the world of IRT, odds don't really exist, so that's fine. Instead, we're going to take the natural log of this odds ratio, and it's that thing there. The natural log, not log 10, this is the difference when you're programming things, of the probability of a 1 over the probability of a 0. That new term in red is what's known as a logit. Now, I've gotten in arguments with people before. I say logit. I've also heard this called log odds. That's probably more common in certain fields, log odds or logits. It's logits. What do you use? Logits? I had an argument with a grad student who insisted that because you're logging it, it's a logit, not a logit. Fine. I've heard logit. I've heard like other pronunciations with the G. Anyone else want to play other words for this? It's logit to me. It's a log of the odds of the probability of a 1. What it does is create a new kind of outcome that is continuous and unbounded. So on the logit scale, for our new red outcome here on the x-axis, I have it plotted against the probability of a 1 on the y-axis. So when you're at 50-50, 50% probability, probability of a 1 is 50.5, probability of a 0 is 0.5, logit is 0. As you move away from that 50-50 mark, the logit changes proportionally. So I think proportionally is not the right word, but symmetrically, that's what I want. So a logit of 2.2 corresponds to a probability of 0.9, whereas negative 2.2 corresponds to a probability of 0.1. So you can talk about predicting the 1, in which case everything is positive, or predicting the 0, in which case things are negative. A logit of 4.6 goes with a probability of 0.99. Can you guess what a logit would be for a probability of 0.01? Negative 4.6, exactly. Logits don't really have inherent meaning. It's really hard to think about what a log of the odds of the probability of a 1 is in any kind of sense. Their purpose is to transform this probability into something that is continuous and unbounded. And in fact, this previous picture that I made, the way that I made this is in a model where I had predicted the logit of the probability of 1 from a linear effect. And this is what it translates to when you back transform logits into probability. The logit goes on forever, the probability does not. So here's another picture that I stole from Snyder's and Bosker's multi-level book, actually, that I really like, because it shows how this shutting off process works. So at this midpoint here, a probability of 0.5 corresponds to an odds of 1, which corresponds to a logit of 0. That's the midpoint. as you move over in logits, as you go from 0 to 1, 1 to 2, 2 to 3, those are equal interval changes in the predicted logit, but how that corresponds back to probability is unequal. So you move from 0.5 to 0.73 for a 1 unit change. The next 1 unit change from 1 to 2, though, goes from 0.73 to 0.88. And the next 1 unit change goes from 0.88 to 0.95. And the next one would be something like 0.98. So the logit can keep being predicted higher and higher and higher, just like a linear model is going to do to it. But when you back translate that logit into probability, probability stays between 0 and 1 like it's supposed to. So a logit is a device. It's a device that gives the linear model something to predict that can go on forever, and then it can be reeled back into something that makes sense via this, what's known as an inverse link function, or what I refer to as the unlogit. So go from probability to logit is the link function. The inverse link is what it takes to go backwards from logit to predicted probability. So link and unlink. Okay, how are we doing? Can I give you an analogy? Why not, right? So I've talked about this in many classes before. I've told you guys about my experiences at Kohl's Cash and whatnot. Yeah. So we have a standing joke in our household that all of the prices at Kohl's are in logits. The unit of measure on the price tag is a logit because it bears little to no correspondence with actual money. Because you have the regular price, but then you have, you know, your friends and family discount from Thursday to Sunday to get you 20% off, and then you have some other coupon that you found, and then you have some Kohl's Cash, and then you have your bonus buy, and after all of that's done, then you can translate your logits into actual dollars. So what I usually do, to at least to get a starting point for how much things are actually going to cost, is take the tag over to the beeper, as you would call it, the price check machine, which I call the inverse link function, because it goes from logits to actual money. And then you can figure out how much it costs. So why are logits useful? Because they can be stretched and shrunk at will. If you need people to go buy more stuff, the price tags stay the same. The signs as to how much percent sale is off change. Right? It's just a device. So logits really don't have inherent meaning. They're a device that makes it so that we can use the same kind of linear model where the slope goes on and on and on and on, and somehow have it understand that what you back translate to does indeed shut off at the ends. So the logit is our friend. So problem number 1, the idea that we need the model to predict a nonlinear slope. By predicting the logit of the binary answer with a linear model, that translates into a nonlinear model in predicting the probability. Yeah. So I don't have it in here yet, but there is a formula that you will grow to know and love to go back and forth. So to unlogit, its probability equals e to the logit over 1 plus e to the logit. And it's on my slide, which is why I'm writing it on the board. So you can always go back into probability. So the order of operations is the tricky part. What you end up doing is taking the predicted logit from the model and then back translating that prediction. So the model linearly predicts differences in the logit as a function of your predictors. You then take those predictions and unlogit them back into probability. So that's problem number 1 solved. The link function makes our slopes nonlinear, makes them shut off like they're supposed to in predicting a 0 or a 1. Problem number 2 is the variance. So in binary variables, they are characterized by a distribution in which there is only one value, p, the proportion of people that got a 1. The variance is then determined as a function of P. It's the proportion of people that got a 1 multiplied by the proportion of people that got a 0. So if you have 50-50 split, your variance is 0.25. If you have a 90-10 split, your variance is 0.09. The end. It's determined. And not only is it determined, it's non-constant. It shrinks the closer you get to the boundaries. It has to. So when you think back to this idea of what a linear model you're used to says E should be, such as in CFA, such as in linear regression, what is this E supposed to be? There's 3 things, right? I'll do one of them for you because it's still true here. Independent. What are the other two? Normal, and one more. Fancy word starts with an H. Yeah, there you go. They need to be homoscedastic. In other words, constant variance. The error around the prediction doesn't depend on what the prediction is. It's constant. That can't happen when you're predicting a binary outcome. So the idea that we could use a normal distribution to quantify these E's isn't going to work. They're not going to be normal because each E can only be one thing. It's either how far off it is from the actual 0 or how far off it is from the actual 1. So there's no way to make a distribution out of that. And the E's can't have constant variance because of this property. So what do we do instead of using a normal distribution for E? We pick something that works better for binary data. Meet Bernoulli. So what I think is funny about these formulas is that normal is what everyone is taught first, like Stat 180, your very first exposure to anything. They talk about the normal distribution. That formula is like one of the hardest ones. I still don't have it memorized. I probably never will. But I'm okay with that. In contrast, Bernoulli is this little thing right here. It is the probability of a 1 if you got a 1, or the probability of a 0 if you got a 0. That's it. Because we know in reality what you got. So the model, the height, if you will, is just the height of whichever one you got. So here's an example of what a Bernoulli distribution would look like if P was 0.25. That's the blue line. If the probability of a 1 is 0.25, what is the probability of a 0? 0.75. It's amazing. It's very straightforward. So this is what we say our data are distributed like after controlling for whatever predictors we have, which is going to include factors in this case. So because there is no variance term that is applicable here, each item is no longer going to get its own residual variance. It's gone. It's not estimated. It's not constant. To complicate things, when you look at the same type of model across sources, you may see it written in one of 5 different yet equivalent ways. And I was really irritated when I finally figured this out, that all these things were the same. Because it's like, why? I'm not good enough at algebra to figure out the reason why this is true. I'm willing to believe whoever figured it out. It was too long ago, and I didn't care at the time because I was going to be a psychologist. I didn't need math. Ha ha ha. But I digress. So of these 5 ways, the top is my favorite. Once you get your head around the idea that what you're predicting is the logit, as y, everything that follows on the right side of the equation is your friend, the linear model. Beta 0 is my intercept. This is the expected logit when x and z are 0. Beta 1 is the change in the logit for a 1-unit change in x. Beta 2 is the change in the logit for a 1-unit change in z. So this is handy because all of the things you learned about main effects, interaction terms, fixed effects, random effects, all that stuff follows once you get your head around the idea that you're predicting logit as opposed to the original raw outcome. So when I'm interpreting parameters fixed effects, for instance, I would do it this way. Talk about what these things do to the logit. When I have to then explain to people what the predictions look like, logit is a terrible decision for a y-axis. No one knows what the hell a logit is. Even people who know are like, so it's a 2? Like, what? So that leads us down the stream here. Let's take the log off then. Let's unlog it. And then we're left with just the odds. And then you get these things in terms of odds ratios. And I cannot handle this one. I just can't handle the fact that you can multiply these things together in a linear model. I just can't handle it. Odds are very common because they help convey effect size. They are not going to be relevant for us in the world of IRT. What is going to be terribly relevant is this down here. And this is the formula that I just wrote on the board. To go back from a logit to probability, if you want to describe how the model directly predicts probability, it's E to what was in the linear model for the logit plus E to what was in the linear model for the logit. Or if you do the algebraic rearrangement, you can simplify the formula into this version right here, where you stick a -1 inside the predicted logit. So this is less typing if you have to write out your model in some software. So here is one of the big differences between the world of IRT and IFA. They are the same. They are two equivalent versions of the same idea of a logistic regression type model predicting item responses from a latent trait. IFA models are written in the top. They predict the logit. IRT models are written in the bottom. So it makes it hard to compare the two. In addition, the way that they describe this parameter, which is going to be the intercept, is different in the world of IRT than it is in IFA, but they are algebraically rearrangeable into one or the other. The slopes are pretty much the same. So I wanted you to have seen this because they are the same model. It's just that the y side is what's changing across, and there's concomitant changes in x. Predicting the probability makes it hard to talk about the slopes in any kind of one-unit change language because they show up inside an exponent and inside both halves of the numerator and denominator. So this is our linear model. This is what we're going to end up predicting. Or this is the predictor. This is what we're predicting on this side. So a logit is the log of the odds of the probability of a 1. And we're going to do that every day until it rolls off the top of your tongue. Okay, how are we doing? What is a logit? Say it with me. The log of the odds of the probability of a 1. Now, why is a logit? That's the bigger question I want you to know. Let me go back to the picture. Why is a logit? You can think of it this way. Because the logit, when predicted, allows for the predictors to have linear effects in predicting the logit. That same linear effect becomes a nonlinear effect in predicting the probability. Logits allow the slopes to shut off. That's why. Homework question. No. Quiz 3. So here's another picture, this idea of shutting off. Now, logit isn't the only game in town. Another way that these models are described is using this terminology of a latent response for the binary outcome. This idea of y star, you will sometimes see things written this way, where y star is the pretend underlying distribution for your binary variable. So it's like your real trait that you're trying to measure with an item response is continuous, like Mayumi's thing here, right? Continuous-ish. And it's like, well, what if I just cut it up and said, no, anything under 50U over 50U. The y star model is ostensibly trying to characterize the original underlying response. So that model gets an E at the end. So whenever you see an E come back, realize that it's talking about not what we're talking about. There's no E's anywhere on our page. because E is not necessary. But this brings up then choices for what our underlying distribution is. So here's a picture I stole from Wikipedia. This is a logistic distribution. It looks a lot like a normal, except that it has a variance of 3.29. So you will see that number, 3.29, show up a lot because it is the variance of a logistic distribution. So if what we're talking about is trying to characterize the variance of a logit, its variance is 3.29. The alternative distribution and link function that you can use to characterize binary data is what's known as probit. A probit is a z-score. Do you remember your intro stat textbook and the tables in the back where you look up p-values and z-values? You can do that online nowadays more readily, but I remember going to those tables and like, what is the z-score that goes with the probability of 0.46? And it's like, That's probit. The probit is the z-score that goes with the probability. So it's the same as logit in the sense that 50-50 is 0. It's different than logit in its variance. Because probit is based on a z-score, its underlying pretend distribution is 1. So this slide sums up why this doesn't matter. I have the pretend distribution up here on the left, in which we have arbitrarily carved it up into our binary outcome. These two models characterize those pretend distributions with different amounts of variance. Logit is 3.29, and probit is 1. Now, there's a reason I keep using the word pretend. We don't know what it is. It's arbitrary. We're never going to know what it is because all we have in reality is the binary outcome. So I could say the pretend underlying distribution has a variance of 1 million, and I'd be right. But these are simply different scales with which to estimate the model in terms of what you're predicting, the link function transformed outcome. You can equate them with a constant of 1.7. So probit scaled estimates multiplied by 1.7 become logit scaled estimates, and this plot shows the difference. Do you see the tiny little deviations between the red and black line? Do you see them? Not very easily, right? So yes, this probit versus logit thing, it's not a debate. In the IRT world, probit is going to be known as ogive. Logit is logistic. But ultimately, there's no right and there's no wrong. They're just different scales. Much like we can have a theta that has a variance of 0 or variance of 10 or a variance of 1. It's different scales. Why you have to know this is because certain estimation choices dictate which scale you've chosen. What we will find out is that when we're using maximum likelihood for these models, you can pick if you want logit or probit. When we use what is known as least squares, which is a limited information estimator such as WLSMV, that only comes in probit. So you have to know what you're looking at to know what scale it is to interpret the estimates. But all the models are trying to predict some kind of transformed response that is continuous and unbounded, that when back transformed into probability behaves like it's supposed to. Okay, how are we doing? Did I not foreshadow, though, that this is going to be a little harder? But the good news is that otherwise you've pretty much learned what you're going to need to know to do this. IRT and IFA are confirmatory factor models predicting logits or probits. That's it. And that's why I teach them in this class. Because when you get to the point where you want to do structural equation modeling, you want to be able to do it no matter what kind of outcome you have. And so a program like M+, which is why we're using M+ and not Lavon, by the way, is you tell it, okay, these indicators are normal and continuous, these ones are binary, these ones are count, and these ones are categorical. Go. And you can fit latent factor models to any of those combinations and then look at relationships among the latent factors. So I like that framework, because then you're not shoved into options that don't apply. That's why we're not using Lavon, because Lavon doesn't have link functions. Or it has logit and probit for binary and categorical options, but only in limited information. That true? Get that right? Yes. So there is no way to do full information IRT or IFA models in Lavon as of right now. That may be different next year, but as of right now, that's why you're learning M+. The terminology, the way the equations work, you're going to have to learn some new words, but otherwise that's the concept. It's CFA predicting logits, because it has to understand that the choice is shut off. And if you know what a logit is for a binary model, then you will understand how it predicts a Likert score too, 1 to 5. What's going to happen is that if you have, say, 5 response options, the program is going to convert that into 4 binary sub-options, such as 1 versus 2, 2 versus 3, 3 versus 4, 4 versus 5. That's one kind. And then the model will give you the logit of each of those categories. So everything runs on logits. Everything runs on logits or probits. So if you get it for binary, you can do it for anything else. And now you look overwhelmed. Or maybe it's just Wednesday. Both? It's okay to be overwhelmed. It really is. This is overwhelming. This is why I'm like, I walked in here freezing and now I'm sweating, because it's like, it takes all of my energy to say these words semi-correctly. All right, questions before we adjourn? No? Okay. I will see you all next week then. Homework 2 is due Friday night. Let me know if you need any help. Ji-Hong also has office hours in here tomorrow from 1 to 4 if you need more time to sit in the lab and get help or get M+. So I will see you all later.